What should we be taking notes on?
Right. So let me give you a steer on that. I should do some expectation management. Actually, the most important thing to observe is that I just pushed this code base to the repo that I advertised onto it yesterday. So yeah, that's a good thing to do. As far away as possible. Right, yes, that's not it. Okay, so
okay. I have the first report. So I think we are ready to go for the final lecture on type theory by Conor.
right. So this is a kind of exercise in archaeology from a talk that I gave longer ago than I care to remember at a Scottish Programming Languages seminar in St Andrews. And it's a kind of progress report on how far I got weaponizing the ideas I was talking about yesterday to get metatheoretic results cheaply. So, I mean, especially if you're not an Agda reader, I mean, even if you are an Agda reader, it's always hard to read other people's big lumps of code. So, as I said, it is available to peruse in the repository. And yeah, what I'm going to try and do is to remind myself of what on earth is in this code base and try to get across the high level ideas of roughly how it works and what I was trying to achieve. And okay, so first of all, actually, I want my other window there. Right, first of all, oh, wrong thing, right thing. Focus does not follow eyeballs, who knew? Right, so this is, I'm starting at where I'm trying to reach at the end. So, okay, one important thing about Agda code when I write it is that anything that isn't a comment, these things are comments. But these things here, right? You see a whole bunch of stuff that's mostly red, right? Red things are canonical data, right? So the high level message is that I have defined a data structure which represents valid rules according to the discipline I describe later. So that is to say that the rules obey all my stuff about information flow and patterns when you receive things and expressions when you send things and all of that stuff about how the subjects of the premises have to cover the pattern variables from the subject in the conclusion. All of that stuff is enforced by definition. So what's happening is that I've got a way in which I could build a type theory, right? This is the fun thing, right? You know, this definition says MLTT is a type theory, right? And and it's a big record in which I say, okay, yes, there are some type formation rules. So I have a separate judgment for being a type in this presentation. Some people were asking about that the other day, yesterday. Yes? Yeah. Well, anything to the right of an equal sign, actually. Here, that's the point, is that I'm just writing down syntax. I'm just writing down data that Agda can compute with. So, I'm not writing down, I'm not declaring inductive data types. I'm just writing down data that describe rule systems. So the whole thing is massively reflected. Okay, and I mean, I'm not expecting what's actually written to make a great deal of sense, which is one reason why I've got comments in the which hopefully present the rules slightly more legibly. But yeah, so I'm to give a type theory, I have to say, what are the type formation rules? So the type formation rules look like something is a type. So here I'm saying the universe is a type. Pi s binding x in T is a type if S is a type, and whenever X is in S, T is a type. And I'm going to throw sigma in as well. So that's just a list of lumps of syntax that represent rules. And what I have to do, I have to say for each type formation rule, the type formation judgment has only a subject. So I have to say, I have to give a pattern for the subject, and then I have to say what the premises are. So that's what I'm doing here. I give a type for the subject, and there are no premises when I'm saying U is a universe. Here I'm saying there's this is a lump of syntax made from the atom pi followed by some pattern S, and then under a binder some pattern called T. Anywhere you see a green oi just means all dependencies are permitted. I'll explain why it means that in a bit, but that's what's going on there. So there's no restriction. The pattern variables are allowed to depend on all of the variables that are in scope. Okay, so same deal with sigma, right? Behind the scenes, the machine is actually checking. This would not be well typed. In fact, maybe I can see if I can mess this up, right? If I simply remove this premise, then what are we saying here? We are saying that to check that sigma st is a valid type, I just have to check S. I don't have to check anything about T. I'm very much hoping that I will get a type error. Right, because it is actually checking. So in fact, you can see it's demanding a proof of so hash 0 is the Boolean value for false, and so reflects the Booleans as a type. So so this is saying, I can't see why this is well typed because, I need a proof of false. So it is actually checking that we're following the rule of having some premise that covers each of the components of the subject. So, yeah.
What's the minimal thing we can get away with here? So, what do we need to show about the non-cover thing to get it to shut up? Yes.
Right. Okay. So the question is, what's the minimal thing we can get away with? Right. So what I'm checking is that every pattern variable which is bound in the subject pattern shows up as a premise, as a subject in one of the premises. So that's to say, everything that to check the whole of the thing, we need to check each of its pieces exactly once. So what happens is, anytime you write a premise that uses a particular pattern variable that came from the subject, that one's kind of ticked off. And we check that by the time we reach the end of the list of premises, they've all been ticked off. Yeah.
So sometimes if I want to write a construct like an impossible, like a pattern match with an impossible case, I get to some. Oh, sorry. So if I was using this technique, right, to write a dependent case split where there's some impossible case somewhere, I would get to some nonsense at some point. Then I can't say anything meaningful about the rest of the patterns that I pattern matched on, right? So will this break, or is there a way of dealing with that? Or is this too technical for this?
That's far too technical. And you know what they say in football? You know, when someone, you know, they say, you know, when someone says, you know, someone's not on offside if they're not interfering with play, but the response is,
I don't know what offside is, sorry.
I'm not going to explain the offside rule in football, but the point is that this is a crap excuse, because if they're not interfering with play, what are they doing on a football pitch?
Well, they came from it.
Yes, you know, so the point is that if there's some lump of syntax that's part of a term, you know, if it doesn't need to be checked, it shouldn't be there. You know, I mean, so what's going to happen in the case where you've got impossible situations is that there will be some syntax which explains why it's impossible, and that's what you have to check about it. So yeah, there's I think it is reasonable to ask that. I mean, it's also the case that you know, you design these systems to say what it is you need to trust about a particular piece of syntax, and that might be trivial under certain circumstances. So as long as you've actually just covered all the things that are part of the term by establishing whatever's the necessary about it, this thing will be happy. Right. So we've got type formation rules, and then I've got, yeah. We need a mic.
I was wondering, you said that all of the pattern variables in the conclusion have to be present linearly in the premises?
In the subjects of the premises.
Yes. How are you enforcing that in Agda? Like, I can't see it in the code.
No, you can't see it in the code. I'll get there.
Okay.
Right. So at the moment, I'm showing you a piece of machinery which which I built using various crazy techniques, and I'm showing you what we can do with the machinery before I show you how the sausage is cooked. Mixed metaphor, dreadful. Anyway, yeah. So I'm just trying to give a high level. You know, I'm writing down the components of a type theory. So I said what the formation rules are. Now I'm going to say how to type check canonical stuff. So here's where I do type in type. I say the universe accepts T if T is a type. So that puts type in type. I've got a rule which says that a pi type accepts a lambda if assuming the bound variable has the domain, the codomain accepts the body of the lambda. So that's the rule we had yesterday. And we also had this rule yesterday, which is that a dependent pair accepts, so a dependent pair type accepts a pair little s, little t, if big S accepts little s, and then T, the big T instantiated with little s, accepts little t. So that's dependent pairs. And okay, high level, what I have to do now for each type checking rule is I have to give a pattern for the input, which is the type that we're checking. And I have to give, as before, a pattern for the subject, the term being checked. And I have, again, I have to give a list of premises. And again, what happens, same deal, any pattern variable from the subject pattern has to be checked in one of the premises. But the other good news, as happens remarkably here is that once we've checked little s, it's checked off as one of the pattern variables we need to cover, but it's added to the collection of variables we trust, which is how come I can refer to little s here. So there's a whole bunch of very careful scope management going on where when you use a subject pattern variable as a premise, it becomes out of scope for more subject activity, but suddenly in scope for everything else. Right, that means it is being moved from being a subject to being a citizen. And all of the other references are to the actual meaningful thing. So again, 3 components to a checking rule, a pattern for the input, a pattern for the subject, a list of premises that have to cover the stuff in the subject. Okay? I'm hoping you get the general impression that, this looks a bit like a pie type, and where you see backslashes, there's variable binding. So this is some backslashes for the lambda, and this t is the body of the lambda. You see question marks, that's introducing a pattern variable. And it was one of those things, you know how it is, you got a pile of code, you're going to give a talk about it, you're going to give the talk about it in like 20 minutes time, and you're sitting in the previous talk completely rehacking the whole thing. So I was sort of there, St. Andrews, keyboard on fire, hacking the presentation of pattern variables so that I could use strings for them instead of pointers. So in a vain attempt to make this even remotely readable, which I concede it is not. Okay. So then next up, we've got the elimination rules. So elimination rules are a wee bit more complicated. So you have to specify, so an elimination rule always takes the thing being eliminated and some lump of syntax which says how it's to be eliminated. So the first thing you do is you synthesize the type of the thing being eliminated. And now you need a pattern to say what sort of types this rule is talking about. So this is the application rule. It expects the thing being eliminated to have a pi type. Okay? So then we need to have, so this thing is always a variable. This thing here is just some lump of syntax. So I have to give a pattern for it. So this part of the subject is the eliminator. So for application, that's just any old shit, right? So I would just write a single pattern variable because the whole of the thing in the eliminator position is going to be used as an argument. Okay, then same deal. I have to give a bunch of premises which cover all the things in the in this eliminator. So in particular, I have to say how to type check S, and I check that little s lives in big S. And then I give an expression which says how to compute this result type. And it's in this expression that I'm allowed to do a substitution. So this question mark minus operator is take the thing called t and substitute its bound variable with that thing. So anytime you see a pattern variable, it's always it always has a substitution attached that says how to instantiate the variables it's allowed to depend on. So here, for example, the substitution that little s is attached to is empty, whereas here, because t is under a binder, I have to actually substitute for the bound variable. So this is computing this type here. And I've got 2 rules for projections from sigma types. So here, so my projections for the for pairs are just atomic symbols, which I label car and coulter because I come from the 1950s. Right.
Could you just remind us what the OI does exactly?
I can tell you approximately and be more exact later, but when a pattern variable is in scope of some binders, you are allowed to write a pattern which says, I'm going to reject things which make use of some of these variables. So, like, for example, imagine you wanted to write a pattern that was describing an eta redex. So you want to say, I've got lambda x and I've got some function which doesn't use the x and then the variable x itself. So if you want to exclude dependency in particular places, you are free to do that. And what the OI means here is no restriction on dependency. So in particular, you can read this as under this lambda, T is allowed to depend on the variable being bound by this lambda. So yeah, OI means all the things in scope. So here, this is all none of the things in scope. And here, it's all one of the things in scope. Right. So yeah, just sort of working through the rules. If we do the car projection, that gives us something of the first component type, that's S. If we do the coulter projection, we get something of type T instantiated with the car projection. So instantiated with the first component, which noticeably means, you know, I actually have to be allowed to talk about the thing being eliminated in the type of the eliminator. It's the first time we've seen a rule like that, where the thing being eliminated shows up in the type that we get by doing the elimination. And in general, you would expect that. You expect that, for example, when you're doing induction on a natural number. You expect the type that comes out of that to depend on the number. So I have a setting which allows elimination rules to talk about the target of the elimination. I mean, sorry, it's one of those things. During my PhD, I needed to do a whole bunch of kind of naming of parts with respect to eliminators. And you know, what is the thing that gets eliminated? Well, where I come from, that's a target. Okay, so everything. So these patterns are real bit lumps of syntax, which, you know, so I have to do a whole pile of implementation to actually give them a semantics. We'll get there in a minute. I've completely forgotten what I was doing with universe rules. And it looks like I'm just saying U is a universe, nothing else is. Right, okay. So next, there's some inscrutable stuff. And what I'm going to do is comment it out. Stick a hole in. This is what you do to understand Agda code. You comment lumps of it out to see what the goal was that, you know. Agda code is all answers, no questions, right? So to get the question back, you comment the code out, stick a hole in, and look in the other window. So this absolute classic situation where the useful information is not in the document, right? So this is slightly, well, very inscrutable because it's not, partly because it's not properly reduced yet. But what's going on? I am actually, I don't get to choose freely what the computation rules are. Instead, I'm computing from the typing rules what the left-hand sides of the computation rules have to be. So what I've got is, I've got a list of the introduction rules that we had earlier, and I've got a list of the elimination rules, and I've got a function called get redexes, which takes the introduction rules and the elimination rules as lumps of syntax and inspects them to figure out which beta redexes can possibly exist. So if I actually normalize this goal, then it's a bit tricky to see, but we get a list with 3 things in it. The first thing says, oh, I found that the checking rule for lambda overlaps with the elimination rule for pi types, overlaps with the application rule. So there's a beta redex when you apply a lambda. And there's a whole pile of stuff. Next element in that list is saying, oh, and I also found that there's an overlap between the introduction rule for pairs and the eliminator for car. And furthermore, I found that there's an overlap between the introduction rule for pairs and the eliminator gooder. So these are the 3 things you have to say what you're going to do with. So that's the high level picture there. Now we've got to see what do we know as to why that's even possible. So I fill in the things. What if I? Right. I need it to like that and like that. Okay, we're back in the room. Thank goodness for that. Okay. Yeah, so that's the point, is that you don't make computation rules out from thin air. You make computation rules up from the possible interactions between introduction rules and elimination rules, right? And crucially, what's going on, see if we can get the 2 things in the same place. Yeah. Crucially, here's a type, here's a pattern for the type when we're checking a lambda. And here's a pattern for the type that we synthesized for the target. And the reason why this beta redex exists is that these patterns unify. So one thing I have to be able to do is to take 2 patterns and ask, when do they both match? That's to say, I need patterns to have most general unifiers. So how do we even phrase that? Maybe I can even try to find, I should show you what a pattern is. Right. Which might also get us somewhere. So I'm going to sort of do dive into more and more detail. So we can, yeah.
I have a question.
If you have a microphone. Yes.
This is about the previous skill. Thanks. So yesterday you told us if you were going to do something clever about judgmental equality, that will come on the convertibility rule.
Yeah.
How would that fit in here?
Well, at the moment, not. This is.
But do you have ideas how to make that fit?
I mean, so this is for a very definite, just with beta. Right. So one of the things I don't in this particular presentation, the change of direction rule being based on syntactic equality is baked in. So I do need to generalize that to get more done. But I was just trying to get a bit of juice from kind of just generally being able to write down a list of rules as syntactic objects that I can compute with.
Thanks.
Yeah. Okay, so here are patterns. So every atom gives you a pattern. Yep.
I lost it somewhere, but to have a bigger picture of what you are trying to say, is it like you are trying to say that how to use typing judgments like the type theory rules that inform us to form reduction rules by combining different combinations of introduction and elimination.
Yeah.
So first you define the typing rules, then So instead of going to reduction theory first to define the typing rules, then using that to like form that.
The only way you can form beta redexes are to have a well-typed elimination of some introduction. So the point here is, you know, I build these rules out of data, and then I can compute from the data when the beta redex, or which beta redexes exist. So yeah, here I'm saying, you know, this won't come as that much of a surprise. There are atomic symbols. Secretly, they're natural numbers, which is why my file had a whole pile of, you know, it's like C programming where you build an enumeration using hash define. And so atoms are patterns. Atoms match only themselves. You can pair two patterns together. So P and Q matches pairs, where if P matches what's on the left and Q matches what's on the right. You can go under the lambda pattern matches only lambdas. These are well scoped, by the way. So I write scopes as SNOC lists, and there are SNOC lists of unit. So this gamma extended by empty tuple, gamma extended by void, means there's another variable in scope. So under a lambda, there's another variable in scope. Right. And then the question marks indicate a pattern variable, which takes a string so that you can refer to it by name. But the key business is saying that of the things in scope, gamma, I am going to permit dependency only on some subset delta of them. So this thing, which we might get to in a bit, delta, you can read as delta as a subset of gamma. I'm terrible. I hate Unicode, so Greek letters have two-letter Latin abbreviations. Right. So this is theta the thinning explains how the variables you're allowed to depend on embed in the variables that exist. So thinnings are otherwise known as order-preserving injections, and thinnings have an identity. So the order-preserving identity is OI. Right. Yeah. So these are patterns, and so one thing I've learned in my life is that you shouldn't use that kind of the spirit of the Brown indexing is pointing into the structures that do variable binding. You're pointing to the binder, right? The Brown indices are only numerical because lambda glues on one binding at a time, giving a natural number structure to the way your collection of variable bindings works that you need to point into. If you're binding whole patterns of stuff, then for goodness sake, don't count the pattern variables. Refer to them by giving a path to them. So this is how inside to refer to a pattern variable. It's actually really given as a path from the root of the pattern to some particular place where there are question marks. And then this was the thing I spent, minutes hacking. I thought, okay, but I don't really want to give paths into patterns to talk about stuff. I want to refer to it by name. And I realized that I could write a thing which would look for the string and compute the path if the string was present. Yep. Right, just give Ohad the mic. Otherwise, I will lose my entire, lecture to waiting for Ohad to ask a question, and then Ohad asking the question, and then me answering the question.
Just when you're waiting for the microphone to arrive, not for me to ask the question.
Yes.
So you're not creating a context of meta variables, which means now you have to index everything by the pattern. Is that
Right? So what I'm saying is the representation of the context of meta variables is nothing other than the pattern itself.
yes?
Yes.
I know, but
Yeah.
is that not screw you over later?
No, in fact, quite the opposite.
Okay, so you're gonna use that.
Yes.
Looking forward to that.
Yes. Okay. There's so that's right. There's some stuff I want to look at. There's all of this pointing business. Right, this is a whole bunch of stuff that does scope manipulation, which I don't want to get into. What I do want to get into is I've got a definition of what it is for a term to match a pattern. So this is the specification that says, hey, if the pattern's an atom, the term better be an atom. If the pattern's a pair, maybe I'll move this. Maybe it won't let me.
No, you had it. Go down. Next to the pie. Left. No, left.
No.
Yes, sir. There you go.
Okay. Maybe I should just do Control C, Control X1. Yeah. So this is basically saying that the point here that if the pattern's an atom, the term better be an atom. If the pattern's a pair, the term better be a pair, and they should match component-wise. If the pattern's a lambda, the term better be a lambda, and what's underneath needs to match. And then what's this saying? It's saying that, morally anyway, that if the pattern's a pattern variable which only allows a particular subset, then as long as the term only uses variables from that subset, you're fine. So that's a sort of specification of matching. And now I have to panic because I don't know which file I put the next bit in. Yeah, it's this file. This is the good stuff. Okay. Is that legible? Ain't as much as reading it would do you any good. I define what it is for one pattern to refine another. So this is an inductive definition of pattern refinement. So that's to say that patterns are the objects of a category, and these are the morphisms. It's about what it is to be more specific than something. So what happens? To refine an atom pattern, you can refine an atom pattern only with an atom pattern. You can refine a pair pattern only with a pair pattern, and the corresponding components must be refinable. Likewise, lambda, but you can refine a pattern variable with any pattern as long as the scope restrictions are obeying. So what we're saying is that refinements of patterns replace pattern variables with something more specific. And that gives you a notion of morphism between patterns. And we have to show a bunch of stuff, but more crucially, well, several things. We need to know that it literally is the case that any term which matches a more refined pattern matches to the less refined pattern. And also, here's the crucial thing, that pullbacks exist. So what I do here is I add a pattern called fail. So I say a maybe pattern is either a thing called fail, which doesn't match anything, or it's an actual pattern. And then I need to show that if you give me two patterns, I can compute the best refinement of both. So I show that I'm essentially doing the pullback construction for patterns. I'm saying I can find, if you give me two patterns, then I can give you a single pattern that matches if and only if both the two patterns I started with match. And I can prove that universal property. So here we're saying, yeah, if we actually get this unifier, then anything which refines both refines the unifier. So that's what we're actively making use of universal properties in building this this machinery. So what's going on with so I'm using this unify to match the pattern in the introduction rules with the patterns in the elimination rules and see which things actually fit together properly. When?
So this is the exact same construction giving you equality on terms from the primitive production relation repeated with the morphism for patterns to give you unification. Or
so that, I mean, equality in terms is kind of on the nose.
I mean, the
Yeah.
way that you extend equality on terms with reduction to get like renormalization and then equality, but
Yeah. Right. So I've got two separate things. I need to consider how to unify two patterns, and I also need to consider how to match a pattern with a term. So beta reduction is done with the latter, but figuring out which beta redexes exist in the first place is done with unification.
my actual question was, sorry.
Yeah.
To what extent is this meta theory tied to the theory that you're formalizing? Like, obviously, it ties into lambda itself. How much of the rest is the lambda here just the concept of binding?
Yes.
Or, okay, so you don't have, if you want to extend it with other stuff, you likely won't have to modify this anymore.
Yeah. So that's kind of the point. So yeah, don't have much time left. So where shall I go next? I'm going to go to a file called stab. And again, I don't expect this to be legible, but it's got a whole bunch of stuff which says everything in sight is stable with respect to thinnings. That's to say, with order preserving injection on scopes. So it's just a whole pile of theorems which are boring as hell, saying you can just chuck more variables into scope and everything still works. And then once you've got that under your belt, wherever it's hiding, this thin, and then there's a whole other module which says, and guess what? Everything in sight is stable under substitution. So here, because I hadn't woken up to the good way to do things yet, it's the usual deal where because you need to thin stuff to go under binders with the Brown indices, you have to prove a load of results about thinnings before you can push your results about substitution under binders. And so yeah, so this is the thing which says, we can show absolutely everything, ending up with, entire typing derivations are stable under substitution, right? So that's built into the framework, right? When I said, if you build typing rules in this way, they will always be stable under substitution. This is that being done at the meta level once for all. This is not a proof per type theory built in the system. This is a proof for every possible type theory expressible in the system. Stable under substitution. And right, so let's see. So there's somewhere I say what the rules are. But this is where I say what a type theory is. And there's a whole bunch of stuff which is actually hilarious, where I'm I'm demanding these collections of rules, and I'm insisting that we are figuring out what the redexes are and then demanding what the reducts are. So for all redexes, I want a reduct. And then we're doing a whole bunch of computable safety checks. So we're checking that the rules are unambiguous, that they're syntax directed. And we're checking that we got no ambiguity in the computation rules either. And then somewhere along the line, this is single step reduction. This is parallel reduction that I talked about yesterday. And somewhere further down, well, okay, these are the rules that you can't do anything about. So this says you can, this is the variable rule. This is the rule for radicals. And this is the rule for the change of direction. It says if you want a t and you've got an s better be equal to t. And here's computing a type before you check it, and this is computing a type after you synthesize it. So all of that's baked in. So you're really only choosing, which types exist in the theory, what their formation, introduction, elimination rules are. Okay, I'm going to figure out what the hell I'm doing by using grep. No, hang on, that's not the right thing. I want to use grep. Call grep first. Right. Oh, grep is in this thing about, there's a whole bunch of stuff about parallel reduction. Okay, so this is reflexive transitive closure and a whole bunch of stuff involving that. And then all sorts of lemmas about parallel reduction. Here's all of that kind of strict lemma stuff. And then there's a general result which says that, again, once for all, if all the safety checks pan out, these systems are confluent. So that again, so I'm just showing you that, so yeah, I do that. So the confluence is again a theorem that you get for the price of writing down rules that make sense in this system. So that's for free. And with a few minutes to go, actually, I wonder if I go back to the Martin-Löf type theory file, so you can see if I ask what's the type of foo, that's not very healthy. What's the type of foo? The type of foo is that if you have a step from t to t0 in the transitive closure of single step reduction, and a path from t to t1 in the transitive closure of single step reduction, then there is some term where you can get from t prime, where you can get from t0 to t prime by multiple reduction steps, and from t1 to t prime in multiple reduction steps. So we just put in data that makes sense. We do no extra work because all the things we need to check are decidable. We can just run those tests, reasoning about the lumps of syntax we built the rules from, and get for nothing a confluence result. Okay, so the prospectus, the thing I haven't got to yet from here, this feels like Everest Base Camp as far as I'm concerned. Yeah.
Right. Can you give
by stability of substitution, you meant to say that like substitution preserves typing, right?
Yeah,
So, I mean, if you are talking about typing derivation, so, so if I'm using the more traditional approach of type theories, like, I need a separate proof for that, like all those thinning and all those things. By this, are you meaning to say that we don't need a separate proof? It is, I mean, that theorem, like substitution preserved typing is correct by construction itself.
Yes.
We don't need a separate theorem. Oh,
Yeah.
Yeah.
No, job done. So yeah, base count, we've got stability under substitution. We do enough checking to make sure we've got confluence. But the thing I really want to get, and that is still part of my ongoing mission, is to get the result which says that if your reduction rules type check, then you have type preservation. So that's to say, here I'm writing down what the reducts are. It ought to be the case that if these reducts have the same type as the redex, then I'm done. You know, we've got type preservation because we're in the form that I stated yesterday, where on the input side, the devil is allowed to choose some computation, and the output side, you're allowed to choose computation that copycats whatever the devil did on the input side. So that's my mission. This is my sort of exploration, not in formal meta theory, but in formal meta theory. Right? I want to prove that to contradict Andy Pitts's observation that type preservation proofs are 2 a penny, that, if you're even paying a halfpenny for a type preservation proof, you're paying too much. So that's, I mean, what was it Whitehead said about, civilization advances by reducing the number of things we need to think about. And, I'm basically trying to re-engineer the discipline for writing down systems of typing rules so that type preservation moves into the category, so the class of things that we that we don't need to prove, that we just need to not fuck up. Okay, that looks like, well, it's 2 minutes to, so I'm happy to take more questions, but I think I've said what I need to say.
Any more questions?
Thanks. So the notion of reduction you have there is the reduction you do doing type checking, to justify conversion and so on. But if you wanted to do the kind of reduction you would do on closed terms at runtimes, then it's a different kettle of fish. Can you do something there too?
Well, so it's one of these situations where, I mean, I can, of course, talk about what it is to be a closed term. I mean, everything's well scoped. I can see where the lambdas are. There's nothing stopping me computing from the open reduction rules what the corresponding closed term reduction relation is. So I could have that by return of post.
No, but there's some reductions you wouldn't do at type checking time, right? So if you were doing like a probabilistic calculus, right, you would not making probabilistic choices doing type checking, which you would do it at runtime, right? So it's a different relation altogether.
Yeah.
And it's not going to be confluent. So you're going to have to.
Let's take that option.
Yeah.
Conor, I'm sorry. Yes.
I'd just better say nothing at all. You don't know when you're well off. So, Yeah, yeah. I mean, so it is always the situation where, absolutely, what happens with open terms during type checking is as much algebra as we can figure out how to do, whereas what happens at runtime is arithmetic. And it annoys both you and me that that the current, for the last 50 years of Martin-Löf type theory, the approach that type checkers have taken to algebra is to keep doing arithmetic until they trip over a free variable and then swear loudly. We have been turning up to an algebra fight armed only with arithmetic. That's got to change. So yeah, we're in a situation where kind of trying to say, well, the computational behavior, it's done the same way in both places. There are just some free variables which will annoy you if you meet them. You're right that that's not sustainable to some extent. I'm in the process of trying to get something basic happening before reaching for more. Yeah, early days.
That's helpful copy.
Good plan. That's okay. Stop sharing and quit Zoom.